Okay, so in this section we need to solve for x, and it involves equations that have the absolute value of x, as you see here. And so the idea here is to isolate the absolute value of x by using some algebra to undo some things, and then when you do that, you will get to be able to use the property of absolute value to solve for x. So we begin with, as you can see here, this is divide by 2 on the left-hand side, so we multiply by 2 on both sides so that you can get rid of that denominator. And you end up getting 5 minus absolute value of x equals 2. And then isolating the absolute value of x, we have 5 minus 2 is equal to the absolute value of x, so 3 equals the absolute value of x. And then once you have it in this form, there's only 2 values that 3 can take. And here you can see that this means, that means that x is either positive 3 or negative 3. And that is how you solve these particular equations. Now in the next problem here, which I have written down below, this is slightly different because it does involve the absolute value of x, but it also just involves x on its own without absolute value. So what I wanted to do was to have you think about what this equation really is you have on the left-hand side, you have one function, and on the right-hand side, you have another. And in some sense, you're setting those two things equal and finding out what x values do these two functions meet at. And so I'd like for you to consider graphing these two things. In particular, let me go ahead and try to graph. I'm going to graph the green function here, underlined in green. Now that's the 4 minus absolute value of x. And if you think about what that graph would look like, it's the absolute value of x looks like that v, right? But then if you do negative absolute value of x, it's kind of the upside down v. And then with the 4 minus absolute value of x, you have it moved 4 units up. So this is sort of exaggerated here. There. So this is roughly what the graph on the left would look like. And now the graph on the right, I'm going to scooch this down a bit. The graph on the right-hand side is similar in the sense that it's just a line, y equals 2x plus 1. And so if we were to graph y equals 2x plus 1, that is a line with slope 2, so, and it's up 1 unit. So if I go ahead, I'm just going to go ahead and try and do what slope 2 looks like. That's like slope 2. Okay, and I'm going to move this so that it has y-intercept at 1, roughly. Okay, these lines are really, really thick. But my point is that if you look at these two graphs, there really is only one place where these two graphs intersect, and that's right there at this value. And you can almost guess what that value would be just by looking at it, that it would be 1. But I'd like to try and work this out not only geometrically, but also using some algebraic techniques. Okay, so this is sort of to give you intuition, and now to try to use the algebraic techniques. Okay. Oops. So again, we isolate the absolute value by rearranging things. And so if I, for example, move the absolute value of x over on that side and then move all of this over to the other side, we end up getting this equation that 4 minus 2x minus 1 equals absolute value of x. Of course, you can rewrite that as absolute value of x equals, and then this simplifies with the 4 minus 1, that gives you 3. So we have 3 minus 2x equals absolute value of x. Now, what is the absolute value of x? By definition, it has two. It's a piecewise function. It equals it equals regular x. Let me write that. If the x is bigger than or equal to 0. And it equals negative x if the x is less than 0. So you have to break your equation up into two cases here. We have, and I'll call maybe this case blue here. Okay. We have that when x is bigger than or equal to 0, then this equation that's right here, that's here. So what do we get? Well, we get that the absolute value just can be written as x, and then that equals 3 minus 2x. So let's try and solve this equation. And as you can see, this equation gives you 3x equals 3, so x equals 1. And then you do a check. The check is x equal to 1 in this domain? So is this value in here? And the answer is yes, right? X being 1 is bigger than 0, so this is a valid solution. All right. So since that's a valid solution, we move on to the next case. So let's look at the next case. Even though geometrically we kind of know what happens, we know that there is no other solution, but let's talk about a little bit like why. So you have that second case. Let me write it here in red. Okay, that second case is when x is less than 0. So if x is less than 0, now what does our absolute value look like? Our absolute value looks like negative x, right? I'm replacing what this means by what it is while x is less than 0. So I'm just doing a replacement. That's what I wrote here. And what does that equal? That equals, so let me just erase that here. It equals 3 minus 2x. Okay, so setting those two things equal, we go ahead and solve it like a regular linear equation. So I can, for example, bring this minus 2x over, and we end up getting that 2x minus x equals 3, so x equals 3. Now what do? We check. We check to see, is this value in here? Is this a valid value? And of course, x equals 3, that's bigger than 0, not less than 0. So in this case, we have a no solution, right? And so in fact, those are the only two cases to check. And so we only have that x equals 1 is a solution.